Right, so we introduced the logarithmic function yesterday. And of course, the main part of our course, being a calculus-based course, is we want to know how to perform calculus on these new functions. So first of all, let's look at how we differentiate logarithmic functions. So if you got y equals the log of some function, the derivative is quite interesting. It turns out to be, you differentiate the actual function, put it on the top of the fraction, and then the actual function that you're logging goes on the bottom of the fraction. So it's like the derivative on the function of whatever we're logging. Once we look at exponentials, I can sort of prove that. A bit hard to prove it at the moment. To generalise it, because of course notice that's a natural base. So I didn't put a base in there, so we assume that's if it's a natural base. If it's any other base, we still do it the same way, but what we also do is on the bottom of the fraction, we multiply it by the natural log of the base. That's why it didn't appear in the first one, because the natural log of base e, well, log e base e is just 1, so it doesn't appear in the derivative. But in any other base, on the bottom of the fraction will appear the natural log of the base. So then differentiating them becomes quite easy. I mean, the function there is 3x plus 5, so the derivative is 3 on 3x plus 5. Differentiate the function, 3, over the actual function, 3x plus 5. The log of x cubed, we could do it a couple of ways. I could differentiate straight up and say, oh, well, that's 3x squared on x cubed. And then, of course, the x cubed and the x squared cancels, and I get 3 on x. But another way I could do it is use my log laws. I could say, well, log of x cubed, that's the same as saying 3 log x. So I could bring the power to the front. Then differentiate log x. Well, the derivative now becomes 1, but 1 times the 3 out the front becomes 3, over the original function x, and as you see, we get the same answer. The log of log x. So the derivative on the original function. So the original function is log x. So we've got to differentiate that. It's a log function. So it's derivative on function. So we end up with 1 on x, because that's the derivative of log x, over the original function, which is log x. That looks messy, of course. So we'll just tidy that up, and we get 1 on x log x. The log of x plus 3, x plus 2. Again, 2 ways you could do it. I could go derivative on function. So when I do the derivative here, I use the product rule. Write down the first if the second, plus write down the second if the first, over the original function, x plus 3, x plus 2. Tidy up the top, 2x plus 5 on x plus 3, x plus 2. Or, again, I could use my log laws and rewrite that as the log of x plus 3 plus the log of x plus 2. And each of those individual parts are quite easy to differentiate. Log of x plus 3, well, that'll just be 1 on x plus 3. Log of x plus 2, 1 on x plus 2. I suppose it depends what you're going to use the derivative for. If I was going to use it to find the slope of a tangent, then that answer is good enough. I could substitute into that, and it works out fine. If it was to find stationary points, well, then I would say, well, the derivative is going to equal 0. I'd have to combine that all into one fraction anyway, and so I'd have more work to do. And when we do combine it, you'll see it turns out to be the same answer. So common denominator, x plus 3, x plus 2. Tidying up the top, we do indeed get the same. So depending on what you're going to do with the derivative, if you use the second idea, is how far you would go. Same sort of thing here. This one, if we do it straight away, well, look what happens, because we've got a quotient rule type question here. So on the top of the fraction, square the bottom, write down the bottom, diff the top, minus write down the top, diff the bottom. But then that's on top of the original function, x plus 5, x plus 2. So I can tidy up the top of the fraction. That becomes minus 3 on x plus 2 squared. Invert and multiply. X plus 2 will cancel with the x plus 2 squared, and I end up with minus 3 on x plus 2, x plus 5. But this one, I think, is where using log laws makes life a lot easier, because I can turn those into two functions which are very easy to differentiate. Log of x plus 5 differentiates to be 1 on x plus 5 minus log of x plus 2, 1 on x plus 2. And again, it depends on what you're going to do with the derivative. I mean, that might be good enough for an answer for what I'm going to do. But even then, combining that into an algebraic fraction, one fraction, we come up with the same answer. I think there's less chance of a mistake in that one with the second way as opposed to the first way. Now, here's one where the base is not e. Remember what we said? We said still do it the same way, but on the bottom of the fraction, we multiply by the natural log of the base. So this will be 6 on 6x, but it'll be times the natural log of 10. The 6's will cancel. I tend to write the log 10 second, so there's no confusion. Because if I wrote log 10 times x, it could be confused to be log 10x. Whereas if I write it as x log 10, there's no confusion. We know that's x times the log of 10. Okay. Now, these exercises, the first one, if I remember correctly, is just on using your differentiation. The second one is curve sketching, and so then finding stationary points and using the calculus to do things.